Welcome to the complete master breakdown of all neuroevolution and reinforcement learning mutation operators. Today we step through every parameter, topology, architecture, hyperparameter, and environment mutation in detail. Applies np.clip to action array, clamping values between low and high limits. Clipping actions enforces physical motor torque limits, preventing dangerous out-of-bounds commands. Clamping action outputs enforces physical motor saturation limits for safe hardware execution. Returns stored previous action buffer tensor instead of current computed action. Delaying action execution forces policies to plan control signals multiple steps in advance. Simulating mechanical lag forces the control policy to anticipate future system dynamics. Returns zero array matching shape of continuous action tensor. A equals 0. Action dropout tests whether the mechanical system can maintain passive stability when power drops. Action dropout tests whether passive physical dynamics keep the system safe during power loss. Multiplies probability array by factor C and divides by sum along axis to restore sum to 1 constraint. Scaling and renormalizing action probabilities boosts preference for specific action choices cleanly. Scaling and renormalizing probabilities boosts target action choices while maintaining valid distribution math. Multiplies output continuous action array directly by scalar multiplier factor C. Scaling action magnitudes tests how well the policy adapts to varying motor power or torque levels. Scaling action commands verifies policy control stability when motor torque levels vary. Returns negative of input continuous action array, A equals A. Flipping action signs tests whether the policy can recover if motor wiring directions are reversed. Inverting action direction tests policy recovery when motor control wiring is reversed. Replaces activation strings with linear based on boolean mutation probability checks. Removing activations creates linear pass-through channels, simplifying representations where nonlinearity isn't needed. Linearizing a layer allows direct matrix multiplication pass-through without nonlinear distortion. Applies logical activation scaling transformation to modify dynamic output range. Scaling activation functions adjust the dynamic range of entire layers without changing weight ratios. Scaling activation output amplitude expands or contracts the layer's overall dynamic signal swing. Applies logical sign flip transformation onto activation function output handles. Flipping activation signs reverses the polarity of all signals emitted by an entire layer. Flipping activation signs reverses the entire output polarity of a hidden layer in a single step. Selects random step delta from K, 0, K, and adds to batch size, enforcing minimum value of 16. Mutating mini-batch size adjusts stochastic noise levels during neural network weight updates. Tuning batch sizes balances stochastic gradient noise against computational throughput. The function identifies 1D bias vectors or single-row matrices and applies Gaussian noise according to the mask. Mutating bias terms shifts the activation baseline of neurons, changing when they fire across input states. Adjusting node biases tunes firing sensitivity across entire neural layers simultaneously. Selected bias vector elements are replaced with new uniform random values sampled between low and high. Resetting bias values revives dead neurons whose activation thresholds have drifted into saturation zones. Resetting bias vectors brings dormant neurons back into active computational roles. Targeted 1D bias values are multiplied by -1 based on the generated Boolean mask. Flipping bias signs instantly switches a neuron from defaulted on to defaulted off behavior. Inverting bias polarity provides high-impact shifts in layer activation profiles. Applies uniform random perturbations from low to high bounds directly onto 1D and single-row bias tensors. Uniform bias mutation provides unbiased exploration of activation thresholds across neural layers. Flat probability distributions allow unbiased threshold calibration across hidden layer nodes. Where the Boolean mask evaluates to true, bias values are set directly to float 0. Zeroing biases forces neurons to rely strictly on weighted input signals without constant offsets. Clearing bias terms simplifies node activation dynamics to pure weighted linear combinations. In Python, we loop through the binary sequence. If a random float falls below our mutation rate, we simply invert the bit. During the process, selected bits invert their state. A 0 becomes a 1, and a 1 becomes a 0. Bitflip mutation is perfect for combinatorial problems. Keeping the mutation rate low ensures we gently explore the discrete search space without losing good traits. When a gene is selected for mutation, instead of a random delta, we forcefully snap its value to either the absolute minimum or the absolute maximum boundary. In many optimization problems, the optimal answer actually lies exactly on a constraint. Boundary mutation ensures the algorithm explicitly checks these extreme edges. While uniform mutation scatters values randomly everywhere, boundary mutation strictly targets the extreme minimums and maximums. Cauchy noise is generated via the inverse transform sampling method using tan of pi times uniform random variables. The heavy tails of the Cauchy distribution allow neuroevolution algorithms to escape deep local minima through sudden long-range leaps. Cauchy mutation enables agents to escape deep fitness plateaus that standard normal distribution noise cannot bridge. Noise is added to weights, followed immediately by xp.clip to enforce minimum and maximum boundary bounds. Clipping ensures network weights stay stable, preventing saturation and numerical instability in deep networks. Enforcing strict bounds keeps weight matrices numerically stable during long neuroevolution runs. Adds normal noise to collision_threshold parameter key in environment map. Mutating collision thresholds tunes how conservatively the policy avoids physical boundaries. Modifying collision thresholds controls how aggressively policies navigate near physical obstacles. Identifies matrix entries with magnitude below threshold and adds significant random weight value. Adding new connections establishes fresh pathways between previously unlinked neurons. Establishing new connections opens fresh communication channels across hidden layer neurons. Generates fresh random weights based on layer fan invariance and replaces selected mask entries. Reinitializing individual weights refreshes stuck connections without destroying surrounding trained weights. Resampling individual weights gives stagnant connections a clean slate to find better parameter values. Randomly selects tuple index, row, col, in target weight matrix and sets value to 0.0. Severing individual connections reduces unwanted interference between features in deep architectures. Severing a single connection eliminates specific signal crosstalk between two neurons. Calls scale_weight_ mutation with low rate parameter to scale targeted individual weight entries. Scaling specific connection weights tunes the relative importance of individual input signals. Scaling individual connection weights adjusts how strongly specific signals influence downstream decisions. Applies sign_weight_ mutation with low mutation rate to invert signs of selected individual weights. Flipping a single connection sign can radically change how a neuron integrates its incoming inputs. Flipping an edge's sign turns an activating input into an inhibiting input for downstream nodes. Applies Gaussian weight mutation with lower mutation rates for sparse, fine-grained synapse tuning. Sparsely mutating individual connections fine-tunes policy details with minimal side effects. Sparse synaptic adjustments make surgical refinements to policy execution triggers. Calls zero_weight_ mutation with low rate parameter to zero out selected individual connections. Zeroing individual connections tests whether specific input signals are truly necessary for policy control. Muting isolated connection edges verifies whether specific signals are essential for decision-making. Adds zero mean Gaussian noise scaled by STD directly to output continuous action array. Adding action noise trains policies to achieve task goals despite physical motor chatter. Simulating actuator noise encourages smooth, fault-tolerant control commands that survive motor chatter. Perturbs gamma with Gaussian noise and clamps results strictly within interval 0.0, 1.0. Tuning discount factor gamma adjusts whether the agent prioritizes immediate gratification or long-term goals. Adjusting gamma shifts the agent's focus between immediate action returns and farsighted plans. Selects random alternative action integer index from available choices, excluding current action. Substituting discrete actions forces exploration across alternative discrete choices. Substituting discrete actions prevents premature convergence on suboptimal categorical choices. Adds normal noise to entropy coefficient C_H and enforces non-negative lower bound max 0.0 C_H. Tuning the entropy coefficient controls how aggressively the policy explores diverse actions. Modifying entropy coefficients prevents policy collapse and maintains exploration in complex environments. Add step delta to epoch count k, enforcing minimum valid epoch count of 1. Adjusting optimization epochs controls sample reuse efficiency versus policy overfitting risks. Modifying epoch counts optimizes data reuse efficiency without overfitting to collected rollouts. Adds normal noise to temperature parameter T and enforces minimum temperature threshold of 0.01. Tuning exploration temperature controls action selection randomness in softmax action policies. Adjusting temperature smooths the transition from exploratory actions to greedy policy choices. Selects random state feature index and deletes corresponding column from observation tensor. Deleting state features verifies if the policy can operate without specific sensor inputs. Deleting a feature permanently removes a sensor channel from the policy's input interface. Generates boolean mask with probability p and zeros out selected state vector entries. Masking features trains policies to maintain control even when certain sensor channels fail completely. Feature masking forces the neural network to correlate surviving sensor channels during partial failure. Generates random index permutation and reorders state vector elements along last axis. Permuting input order tests whether the policy relies on strict feature index placement. Permuting state vector order challenges the network's reliance on fixed input index placement. Selects random feature index in state array and multiplies values by scale factor C. Scaling single features tests policy resilience to miscalibrated or unscaled sensor inputs. Scaling single feature columns simulates sensor gain drift or calibration discrepancies. Selects random state feature column and multiplies entries by -1.0. Flipping feature signs tests how the policy copes with inverted sensor polarity. Flipping a feature's sign tests policy response to inverted physical sensor wiring. Adds normal noise to friction parameter key in environment dictionary. Mutating friction coefficients trains policies to handle slippery surfaces and traction variations smoothly. Altering friction coefficients teaches the policy to manage slip and momentum on slick surfaces. Adds normal noise to lambda and clips results strictly within valid range 0.0, 1.0. Mutating GA lambda controls the trade-off between advantage estimate bias and variance in policy gradients. Tuning lambda balances advantage estimate accuracy against policy gradient variance during training. Adds zero mean Gaussian noise scaled by STD directly to input state vector array. Corrupting state inputs with Gaussian noise ensures policies remain stable when deployed on physical hardware. Simulating sensor noise is essential for transfer from simulation to physical robot hardware. Notice how a random Boolean mask selects candidate weights, and standard normal values scaled by sigma are added in place. Gaussian perturbation is the gold standard for continuous local exploration, allowing weights to fine-tune smoothly. The weight values drift slightly around their central density, maintaining local parameter neighborhood structure. Adds normal noise to goal_position parameter key in environment map. Moving goal targets trains goal condition policies to reach arbitrary target coordinates. Randomizing goal coordinates trains universal policies capable of reaching arbitrary target points. Adds normal noise to gravity parameter key in environment dictionary. Mutating gravity forces control policies to learn fundamental physics rather than memorizing timing. Varying gravity forces the agent to adapt reaction torques to changing downward forces. We start by picking two random boundaries to define a slice of the sequence. We then reverse the order of elements within that slice. Watch how the selected block flips exactly backward. This is distinct from scrambling, because the relative adjacencies within the block are maintained. Inversion is incredibly powerful for the traveling salesperson problem. By reversing a path, it can untangle crossing edges while preserving the connectivity of the cities within the block. Selects random index and activation function list, and replaces string with new choice like ReLU, Tanh, or sigmoid. Swapping activation functions changes how signals saturate and propagate through hidden layers. Swapping activation functions changes whether signals are bounded or unbounded across hidden layers. Creates identity matrix W plus small noise and zero bias vector, inserting them into wait list. Adding hidden layers increases hierarchical depth, enabling higher-level feature abstraction. Inserting identity-like layers increases network depth while preserving existing control policy behavior. Computes matrix product of adjacent layers W1 at W2 and replaces them with consolidated matrix W_new. Deleting hidden layers flattens architecture and reduces compute latency by combining sequential operations. Multiplying adjacent layer matrices together compresses two layers into one without losing linear transformations. Duplicates target layer matrix block, inserting copy to expand depth with identical feature transformations. Duplicating a layer allows the network to iteratively refine its internal feature representations. Cloning complete layers enables iterative feature refinement across repeated processing stages. Replaces target layer normalization string entry with randomly chosen alternative from available types. Altering normalization schemes controls internal covariate shift and stabilizes deep policy learning. Switching normalization schemes prevents internal activation drift across deep neural networks. Swaps weight matrices W1 and W2 if shapes match, reordering sequence of feature transformations. Reordering layers tests whether changing the sequence of transformations yields better feature hierarchies. Swapping same-dimension layers alters feature hierarchy ordering without changing total parameter counts. Loops neuron_deletion k times to compress targeted hidden layer matrix dimensions. Slimming layer width removes excess nodes, speeding up matrix multiplication performance. Slimming layer width prunes unnecessary parallel channels, streamlining tensor computations. Loops neuron_addition k times to widen targeted hidden layer matrix dimensions. Increasing layer width expands the number of parallel feature detectors available to the policy. Widening hidden layers increases the number of parallel feature representations evaluated at each time step. Adds Gaussian noise to learning rate parameter, enforcing minimum threshold of 1 times 10 to the power of -6. Mutating learning rate allows NeuroEvolution to discover optimal step sizes for gradient-based updates. Evolving learning rates balances fast policy adaptation against numerical stability during gradient updates. Multiplies learning rate by exponential of Gaussian noise, LR*exp, Ren*std. Log-scale mutation explores learning rates across multiple orders of magnitude seamlessly. Logarithmic scaling explores learning rate variations across several orders of magnitude smoothly. Adds normal noise to mass parameter key in environment dictionary. Mutating object mass ensures policies remain effective when carrying varying payload weights. Randomizing mass parameters forces the agent to adjust braking timing for heavy payloads. The mutate function loops through weight tensors, creating a random Boolean mask and adding Gaussian noise scaled by standard deviation. First, evaluating uniform random floats against the mutation rate generates a Boolean mask. Only 30% of weights undergo mutation. Multiplying mask with Gaussian noise ensures zeroed entries keep their original weights, while selected entries receive random perturbations. Mutation rate controls how frequently parameters change, while standard deviation determines the magnitude of each exploration step. Adds normal noise to mutation rate PM and clamps results strictly within interval 0.0, 1.0. Evolving the mutation rate meta-hyperparameter discovers how frequently parameters should mutate. Evolving mutation rates automatically tunes how aggressively children disrupt parent parameters. Multiplies mutation strength sigma by exponential of normal noise, sigma *exp, ren *std. Self-adapting mutation strength sigma allows the algorithm to automatically adjust its search step size. Self-adapting mutation strength sigma dynamically tunes step sizes for each individual agent in the population. Appends a new column to matrix W_I, a zero bias entry, and a new row to adjacent matrix W_J. Adding neurons expands the functional representation capacity of the network, key to neat algorithms. The network topology grows dynamically, opening new computational dimensions for complex tasks. Selects a random node index and deletes corresponding column in W_I, bias entry, and row in W_J. Deleting underperforming neurons streamlines the policy architecture and speeds up inference. Pruning removes excess parameters, optimizing computational efficiency during policy execution. Zeroes out specific node columns in W, bias terms, and corresponding row entries in the next layer. Silencing a neuron tests whether its computational contribution is essential to policy performance. Disabling a node silences its signals without permanently altering the underlying matrix layout. Copies column from W_I and row from W_J, appending them to double the selected neuron's features. Duplicating a neuron creates redundant pathways that can independently diverge into specialized subfunctions. Clone neurons allow one twin to maintain current behavior while the other evolves new features. Generates new random normal values scaled by Lacoon norm variance and overwrites selected node columns. Reinitializing a single neuron allows it to learn a new feature from scratch without resetting the whole model. Surgically reinitializing a node gives the network a fresh chance to learn a useful new feature. Targeted node columns in weight matrix W are multiplied by constant factor C. Scaling a neuron's weights boosts or suppresses its overall contribution relative to neighboring nodes. Scaling calibrates how strongly a single neuron signal is broadcast to subsequent layers. Multiplies targeted node columns in weight matrix W by -1.0. Flipping a neuron's incoming weights inverts the pattern it detects, searching for opposite visual or physical cues. Inverting a node's receptive field flips its feature detection from positive to negative indicators. Selects target node columns and adds Gaussian noise vectors exclusively to those selected columns. Targeting an entire neuron's input weights updates its holistic feature detection profile. Perturbing all incoming weights of a single node realigns its feature extraction behavior. The decay factor is computed as 1 minus generation over max generation raised to power b, scaling the noise standard deviation. By annealing step sizes across generations, non-uniform mutation mimics simulated annealing within neuroevolution. As generations progress, the mutation step size shrinks automatically to settle the population into optimum states. Applies np.clip directly to input state vector array using specified low and high limit bounds. Clipping observations mimics physical sensor measurement limits, clamping extreme readings. Clamping state observations reflects physical hardware sensor saturation constraints. Replaces current state tensor with stored previous state buffer tensor. Delaying observations forces policies to learn internal predictive dynamics to handle control lag. Injecting observation delays forces the policy to compensate for sensor transmission lag. If random check falls below probability P, returns array of zeros matching state shape. Observation dropout tests whether the policy can survive brief total blackouts using internal momentum. Total observation dropout tests whether blind inertia control can survive temporary sensor blackouts. Adds normal noise to obstacle_position parameter key in environment map. Randomizing obstacle positions forces policies to dynamically replan collision-free trajectories. Shifting obstacle locations prevents memorization and forces real-time trajectory replanning. Adds normal noise to obstacle_size parameter key in environment map. Varying obstacle sizes trains policies to adapt safety margins to changing physical constraints. Scaling obstacle dimensions forces the control policy to maintain dynamic safety margins. Calls layer_activation_change specifically targeted at actor policy activation list. Swapping actor activation functions allows the policy network to discover optimal decision nonlinearities. Swapping actor activations changes whether policy decision boundaries are piecewise linear or smooth. Calls layer_addition targeted specifically at actor policy network waitlist. Adding layers to the actor network expands its ability to learn intricate policy decision boundaries. Deepening the actor network allows it to represent highly complex control decision boundaries. Adds normal noise vector scaled by STD directly to policy output logit array. Injecting noise into pre-softmax logits perturbs action choices while respecting relative preferences. Adding noise to unnormalized logits smoothly alters final softmax action probability distributions. Adds normal noise with larger STD specifically to last weight matrix in actor network list. Heavily mutating the action head remaps extracted features to new action commands without ruining feature extraction. Focusing mutation on the output head reinterprets trained hidden features into new action strategies. Calls Gaussian_weight_mutation specifically targeted at actor policy network weights. Mutating policy network parameters creates state-consistent exploration trajectories across full episodes. Injecting noise into actor weights produces smooth, state-consistent exploratory behaviors across episodes. Adds normal noise to policy temperature T and enforces lower bound threshold of 0.01. Mutating actor policy temperature controls action randomness without affecting value function targets. Tuning actor temperature adjusts action exploration spread independently of value estimations. The delta parameter is computed conditionally based on uniform random variables raised to power 1 over eta plus 1. Polynomial mutation gives fine-grained control over search granularity, allowing precision tuning in real-valued parameter spaces. Adjusting the polynomial index ETA allows a seamless transition from global exploration to delicate exploitation. Add step delta from k, 0, k to population size n, enforcing minimum bound of 10. Mutating population size balances genetic search diversity against generational computation speed. Adapting population size balances broad genetic diversity against fast generational iteration speeds. Adds normal noise to position parameter key in environment reset configuration. Mutating initial positions ensures policies can balance and control systems from anywhere on the track. Spawning at varied rail positions ensures global control authority across the entire workspace. Adds noise to clip parameter and bounds results strictly between 0.01 and 0.50. Mutating PPO clipping bounds controls the size of trust region policy updates to maintain training stability. Adjusting PPO clip bounds balances conservative stability against fast policy iteration. Adds small epsilon 1 times 10 to the power of -4 to probability array and renormalizes across action axis. Redistributing probabilities prevents non-selected actions from collapsing to zero selection chance. Blending a uniform baseline across actions guarantees non-zero exploration chance for every choice. Calls provided action space sampler function to return uniform random action array. Replacing actions with uniform random samples drives maximum action exploration in unknown environments. Injecting random actions ensures the agent explores unfamiliar areas of the state action space. Where the mask is true, old weights are replaced entirely with new uniform values from low to high. Random resetting acts as a nuclear option for stagnant weights, forcing the network to discover alternative computational paths. Selected entries in the weight matrix have their old values erased and replaced with brand new initialized values. Replaces occurrences of ReLU in activation string list with GELU. GELU activations provide smooth gradients for small negative inputs, preventing dead neuron issues. GELU activation smooths out the hard kink at 0, improving gradient flow during evolution. Replaces occurrences of ReLU in activation list with CELU. CLU activations introduce self-gated non-monotonicity, helping deep policies capture intricate dynamics. Swish activation introduces non-monotonic dips below 0 that aid subtle control decisions. Replaces all occurrences of string ReLU in activation list with Tanh. Converting ReLU to Tanh bounds outputs between -1 and +1, smoothing control signals. Transitioning from ReLU to Tanh smooths output transitions and bounds signal magnitudes. Multiplies or divides replay buffer size M by factor 1.2 based on random coin flip. Mutating replay buffer size adjusts how long historical experiences remain in the training memory pool. Adjusting replay buffer capacity balances historical data retention against stale policy experience risks. Adds zero mean Gaussian noise scaled by STD directly to reward array values. Injecting noise into rewards trains policies to perform reliably even under corrupt or noisy feedback. Adding reward noise prevents policies from overfitting to brittle, specific feedback values. Multiplies input reward array by constant scalar factor C. Scaling reward signals improves numerical gradient conditioning without changing relative goal preferences. Scaling reward magnitudes conditions value function loss gradients for stable optimization. Adds alpha times mean state feature value to reward array. R equals R plus alpha asterisk mean, S. Shaping rewards provides intermediate hints, helping agents solve difficult sparse reward tasks faster. Adding shaped potential signals guides exploration towards distant goals in sparse reward domains. Selected mask entries multiply the weight by factor C, preserving the sign while scaling magnitude. Scaling weights adjusts the gain of neural pathways without altering the basic topology or excitatory nature of connections. Targeted matrix elements are multiplied by factor C, boosting or attenuating their signal strength. The code selects a continuous subrange within the genome, extracts it, shuffles the elements randomly, and inserts it back into place. Compared to a simple swap, scrambling affects an entire block of genes. This introduces much more variation and helps break out of local optima faster. Notice how the outer elements remain completely stationary, while the inner subset experiences a completely random rearrangement. Adds normal noise to sensor_noise parameter key in environment config. Varying environment sensor noise parameters tests policy adaptation to fluctuating noise regimes. Scaling environmental noise variance trains implicit state
filtering capabilities into policy weights. The code uses xp.where with the boolean mask to replace w with -w while preserving unmutated elements. Flipping the sign of a weight instantly reverses its influence on downstream neurons without changing its magnitude. Inverting connection sign tests whether suppressing a signal yields better control policy outcomes. Here is the vector Python implementation for structural _mutate. Applying structural mutate introduces unique variations into the population. This operator alters parameters according to its defined mathematical rule. The implementation is incredibly simple. We randomly pick two distinct indices in the sequence and exchange their corresponding values. We use swapping instead of random replacement because permutation problems require every element to appear exactly once. Swapping preserves this integrity. Observe how selecting the second and fifth items and exchanging them leaves the rest of the sequence completely untouched. Replaces occurrences of Tanh and activation function list with sigmoid. Sigmoid activations constrain outputs strictly between 0 and 1, ideal for probability or gate outputs. Switching to sigmoid maps outputs directly into normalized probability ranges. Adds noise to tau and clamps results strictly within range, 1 times 10 to the power of -5, 1.0. Mutating polyac parameter tau controls target network stability in algorithms like DPG and SAC. Tuning target update rates stabilizes Q-value targets against wild online value oscillations. Modifies terrain string identifier key in environment parameter map. Mutating terrain geometry forces policies to handle slopes, bumps, and uneven surfaces. Swapping flat tracks for inclined slopes forces the policy to compensate for downhill gravity pulls. Adds normal noise to DT parameter key in environment dictionary. Varying simulation time steps prevents policy overfitting to fixed integration intervals. Varying simulation time steps tests policy control stability across changing loop frequencies. The uniform mutate function replaces selected genes with entirely new, random values sampled from a defined lower and upper boundary. Unlike Gaussian mutation, which adds a small delta, uniform mutation performs a complete reset of the variable, ignoring its previous state. While Gaussian mutation takes small local steps, uniform mutation makes large discontinuous leaps, making it excellent for global exploration. Adds uniform random noise bounded between low and high across state vector array. Uniform observation noise tests policy control stability under flat, bounded sensor uncertainty. Testing bounded uniform noise ensures policy stability across all sensor tolerance limits. The code uses random.uniform to generate noise within specified lower and upper bounds, applied wherever the mask is true. Unlike Gaussian mutation, which favors smaller perturbations, uniform mutation samples step sizes with equal likelihood across the entire interval. Comparing the two distributions highlights how uniform noise treats all perturbation steps within bounds with equal probability. Calls bias_Gaussian specifically targeted at critic value network bias parameters. Mutating critic biases shifts the overall baseline offset of value function predictions. Shifting critic bias terms adjusts the baseline offset of predicted return values. Applies np.clip to value prediction array, enforcing low and high limit bounds. Clipping value predictions prevents exploding Q values and stabilizes critic loss optimization. Clamping value predictions prevents value divergence and keeps Bellman updates numerically stable. Adds zero-mean Gaussian noise scaled by STD directly to predicted value array. Adding noise to value outputs tests how robustly actor policy updates handle noisy value baselines. Injecting noise into value outputs verifies actor stability when critic guidance is imperfect. Multiplies output value array V directly by scalar multiplier factor C. Scaling value outputs adjusts predicted return magnitudes and TD error update scales.
Scaling value predictions adjusts temporal difference error magnitudes without altering relative state rankings. Returns negative of input value array VS equals VS. Flipping value signs turns predicted rewards into penalties, testing value estimation resilience. Inverting value signs flips state evaluations from positive rewards to negative penalties. Calls Gaussian _weight mutation specifically targeted at critic value network weight list. Mutating critic weights perturbs value estimates versus exploring alternative state evaluation baselines. Mutating critic parameters explores alternative value estimation baselines independently of actor choices. Adds normal noise to velocity parameter key in environment reset configuration. Injecting initial velocity noise trains policies to recover stability from dynamic starting conditions. Starting episodes with random initial velocities builds strong dynamic recovery capabilities. Adds normal noise to wind_force parameter key in environment force accumulator. Applying random disturbance forces trains policies to actively reject external wind gusts. Injecting continuous force pushes trains the policy in active disturbance rejection. Where the mass condition evaluates to true, weight values are replaced with 0.0 flow precision. Zeroing out weights introduces evolutionary sparsity, encouraging network robustness against parameter failures. The selected synapse is set to 0, effectively muting its contribution to downstream activations. That completes our deep, comprehensive master breakdown of all neuroevolution and reinforcement learning mutation operators. Thank you for watching.